Welcome to the Explainer. Today, we're looking at something that powers our entire world. But here's the thing it works in a way that seems completely, well, wrong. We're talking about alternating current, or AC. So, let's just kick things off with a question that honestly sounds like it's straight out of science fiction. But I promise you, it is happening in your home right this very second. Imagine the electricity flowing to your TV, just slamming on the brakes, and then throwing it into reverse over and over and over, faster than you can even blink. The wild part? That's exactly what's happening. The power flowing through your walls is in this constant, high-speed dance of stopping and reversing. And that little secret is the key to how our entire electrical grid actually works. All right, so to really get our heads around this, we need to stop thinking about AC power as a steady stream, like water from a hose. It's much more like a wave in the ocean, constantly rising, falling, and changing. Now, here in the US, the standard for this wave is 60 complete cycles, up and down every single second. You've probably heard of this. It's called 60 hertz. Just to put that into perspective, try to imagine flipping a light switch on and off 60 times in 1 second. That's the absolutely relentless rhythm of our power. So each one of those 60 cycles actually has two distinct halves. You can kind of think of it like taking a breath. There's the part where you breathe in and the part where you breathe out. In electricity, we call these two halves alternations. So let's do the math real quick. If you've got 60 cycles happening every second, and each one of those cycles has two alternations, well, that means the current fully stops and reverses direction 120 times every single second. And that is exactly what we were talking about right at the start. This constant, frantic reversal makes certain components, like capacitors, behave in a totally unique way. See, in a DC circuit, a capacitor kind of acts like a little battery, just storing up a steady charge. But in an AC circuit, oh no, it's more like a tiny, high-speed switch, charging up and then instantly discharging 120 times a second. It's a completely different ballgame. So you have to be asking, how in the world is this incredible back-and-forth flow even created? Well, it's not magic, not at all. It's pure mechanics, and it all begins with a really simple and honestly elegant piece of physics. At its very heart, AC generation is just a loop of wires spinning inside a magnetic field. That's it. As one side of that loop passes the magnet, boom, current flows one way. As it keeps spinning and the other side of the loop passes by, the current gets pushed in the exact opposite direction. That simple rotation is all it takes to create that perfect repeating sine wave. And that wave shape is absolutely crucial because its rising and falling nature is what lets transformers work, stepping voltage up and down and making long-distance power transmission even possible. Okay, but in the real world, this perfect little wave doesn't just travel along by itself. Nope, it runs into forces that are constantly pushing and pulling on the flow of current. It creates this kind of electrical tug-of-war. So things like motors, they create something called inductive reactance. The easiest way to think about it is that the voltage gets a head start and basically has to drag the current along behind it, making the current lag. But then you have capacitors, and they do the opposite. They create capacitive reactance. They give the current a little bump, a little push, so it actually gets out ahead of the voltage. It's this constant dance of who's leading and who's following. So, let's recap. You've got the normal resistance you'd expect from the wire itself, but then you add this drag from inductance and this push from capacitance. What do you call the total combined opposition to the current? That big combined force is called impedance. It's the grand total of everything fighting against the current in an AC circuit. And what's really fascinating is that this push and pull part, the reactance, it only even exists when the power is on and that current is alternating. So far, we've just been talking about a single wave. But to power our cities, our factories, we have to scale this up in a really, really clever way. So let's talk about the genius of three-phase power. Okay, so instead of one spinning loop generating one wave, I want you to picture three loops, all spinning together but spaced out perfectly from each other. This setup generates three separate sine waves, but they're all perfectly out of sync with each other by exactly 120 degrees, which is, of course, 1/3 of a full circle. And this brilliant little offset has a massive, massive impact on power delivery. A single-phase system, like the one in your house, gives you two little peaks of power for every cycle. But a three-phase system? Yeah, that triples it. With 6 power peaks crammed into every cycle, the flow of energy becomes incredibly smooth and way more consistent. Unlike the power in your house, there's almost no point where the power drops to zero. And that is why three-phase power is the absolute backbone of industry. It delivers that immense, steady torque you need to run all the heavy machinery. So, what's the big takeaway from all this? Well, it's a beautiful irony, really. The very thing that seems like it should be a flaw in AC power, this constant stopping and reversing, is precisely what makes it so incredibly powerful and versatile. I mean, think about it. Without that reversal, we couldn't just spin a magnet to generate power. We couldn't use transformers to step voltage up for efficient long-distance travel and then back down to safely use it. This whole elegant dance of electricity, born from one simple spinning loop, is the invisible engine of our entire civilization. And it all started with just a simple question. What if the power didn't flow in a straight line?